So we have several instructions for manipulating the interrupt context. We have the ability to take the interrupt context and save it into a separate memory buffer and then load it back from that memory buffer. This is typically used on operations like signal handling, where we interrupt a program, we're going to do something with the state, but we want to restore the original state later. We also have the commit operation, which basically takes an interrupt context and commits everything to the kernel stack. And then we have this last function here, which is a little odd. It's LLVM push function. Essentially what it does is it takes an interrupt context and it rewrites it so that this function with this set of arguments appears to have been called. And in this way, this is a high-level way of doing signal delivery. So this allows us to rewrite the state so that when the state is resumed on the processor, it wakes up and is running in this new function with these new arguments. And then when we want to return from the signal, we simply use LLVM context load to load the original interrupt context data back onto the kernel stack. So if this is a little confusing, afterwards I think I have a little animation which may help explain it better. If you're interested, please feel free to see me.
So is there any read on OS using these constants?
Yes. So the operating system must be ported.
Right. So you treat this as like the ISA essentially.
Yes, exactly.
You're a virtualizer.
It's similar to that, except what we're wanting to do is we're wanting to eliminate all inline assembly code from the kernel. So all assembly code is within our virtual machine, not the operating system. So also with state, we have state to manipulate, instructions to manipulate the state that's currently on the processor. We've taken the native state and we divided it into what we call integer state and floating point state. Integer state is the native state associated with any LLVM control flow and integer operation states. And then the floating point state is any state that's associated with LLVM floating point operations. And then with the way that we've designed the floating point saving intrinsics, we've designed them in such a way that the operating system can forego saving the floating point state if it hasn't been modified. So finally, the last thing that I want to briefly talk about is some of the security work that we're doing with this virtual machine. And one thing that we're doing is we're trying to provide memory safety for commodity operating system kernels, such as Mac OS X and Linux. So the first thing that we do is we use static analysis to prove that some memory accesses are safe. So if they're safe, prove it statically. We don't need to insert any runtime checks to make sure that they are safe. However, in real programs, and especially in the operating system, this is only true for a subset of your memory accesses. So the question is, what do we do for the memory accesses that we cannot prove safe at compile time? So the first thing that we do is we use pointer analysis to determine which pointers can alias each other. So in this diagram, the blue pointers can alias the same memory, the yellow pointers can alias the same memory, and similarly for the red pointers. Next, what we do is we have the virtual machine record object allocation. So we modified the kernel memory allocators to essentially tell our virtual machine, here's when I'm allocating a piece of memory, and here's how large it is. And then our virtual machine, combined with the pointer analysis, can tell which objects go in which of these logical pools. So we have a blue pool that points to, that contains information on all blue objects. What's supposed to be a yellow pool for the yellow objects, and again, similarly for the red. So when we do a runtime check, we don't actually need to run through all of the objects in the program. We can just simply check all the objects associated with a particular pool. So if I'm checking this blue pointer, I don't have to check through all the objects. I just check through all the objects that are in the blue pool. And so in this way, we try to do this to increase the performance of our runtime checks. So acknowledgements. This research is basically an amalgamation of several years' worth of research at the University of Illinois. And I won't run through all the names, but I think I got everyone. And I would especially like to note that the LLVM community has been very helpful in the work that we do. You guys have fixed a lot of bugs that have been very helpful in compiling Linux. So we appreciate that a lot.